Okay, so the next talk is towards Minimax optimality of model-based robust reinforcement learning, and I believe it will be presented by Pierre.
So hello everyone, so I'm Pierre, and I will present the work I did with my two supervisors, so Erwan Pennec and Matthieu Geist. So basically, this work is about robust reinforcement learning. So what's the idea of robust reinforcement learning? So in classical reinforcement learning, such as previously, for example, you try to learn the best policy on a given environment, and the law on training and testing are the same. So basically, you're trying to find the best policy to win at playing chess. And after, the rule of chess are not changing when you're trying to win at playing chess. And here, the rules are a bit different. So I will try to learn the best policy on a given environment. And then on testing time, I will change a bit the probability transition, my transition kernel, and see if my policy, my value function generalize well to this slightly modification of the environment. For example, we can think as in 2 weeks, it's like Olympic Games in Paris. And you want to be good at playing tennis, and you are playing tennis only against me. So you learn to be very good against me at tennis. But if you want to generalize you're learning your strategy to win at tennis to other players, you want to learn a good policy in general. So that's why, and I will also talk more about sample complexity. So if you were at the previous talk on Monday, the last tutorials on statistical reinforcement learning, it's really related to the tutorials. So I will talk about sample complexity of this kind of other frameworks called robust reinforcement learning. So, right. So I was saying, for example, here, just to illustrate what I'm doing. So I'm training an agent with a length of pole of 1 and a cart mass of 1 on training, and I'm trying to deploy this strategy, this policy, to a new environment with slightly modification of physical parameters. So here's the length of pole and mass. And as you can see, the performance decreased a lot, just changing a bit my environment. So I would like to be robust to this slightly modification in general with robust reinforcement learning. And about sample complexity, so if you are the tutorial, we saw that the sample complexity was very useful. And also in deep reinforcement learning here, for example, sometimes you don't know why, but the number of samples needed to achieve good policy in state-of-the-art algorithms such as TV3 or SAC, it's a lot of sample, basically billion of samples to have a good performances. So I would like to reduce the number of samples to achieve good sample complexity in general. So yeah, just mathematically, I define MDPs very simply. You have an environment with a kernel P, which you assume it's fixed during training, and it returns a next state S prime given S and A, and you want to compute the best policy by parameter by theta, for example. And you have the discount factor. So here you have infinite horizon, and the object you try to approximate basically is a so-called Q function, which is just the average returned starting from S and A. So here you have just the expectation of all of your reward function, and you would like to approximate the Q star, which is just best Q function, playing the best policy in general. And you fortunately, because how do you approximate it very easily? You can just iterate so-called Bellman operator, which is just an operator, and just iterating this operator, you have a chance to converge to Q star because actually this is a contraction. So just iterating this operator, you converge fastly to the best solution. So this is in classical RL, and Q function is indexed by pi here, which is the kernel. So yeah. How do people proceed generally? They just use evaluation and improvement. So you have one step of evaluation when you try to getting the next Q function given the previous one using this Bellman operator, and you pick the greedy action at every step. And so iterating this framework, you converge to Q star. And one thing which I think it's quite interesting is if you use VI as I just described, you converge without any errors to the right solution exponentially fast. As long as gamma belongs to 0, 1, which is the case in practice. And so, but as long as suddenly when you just impose some errors, so you have, in practice, you have a lot of errors due to, I don't know, you don't know the kernel, so you have estimation errors. You could have greedy errors because you have continuous space, or if you try to approximate in continuous and state action space, you have a function approximation error also. So due to all these errors, you don't have any guarantees of convergence to the right, to the function. So like, as long as you have some errors, there is no convergence guarantees. So because you have a sum of norms of errors, so here, no convergence guarantees. And like, for example, what thing you can do is like regularized with a KL divergence scheme, and you have like more like a norm of sum of errors. So if your errors are centered, maybe you have a chance to converge. But for example, in robust reinforcement learning, you have this kind of errors, which are maybe due to model misspecification, and your errors are not centered. So you don't have any convergent guarantees in practice in reinforcement learning, as long as you don't have the right kernel on testing, for example. So I would like to design some algorithm which are robust to this errors, and see how many samples I need to converge to this solution. So, like the framework I'm using is very simple, so it's not like related to DPRL. It's just very simple. I use generative models where I can sample given S and A n times some sample, some next state, and I construct an empirical MDP using this sample. So just classical mean. And here I'm playing my empirical pi hats and not pi as a question is, so I'm doing approximate value iteration. And the question is, how many samples do I need to get epsilon closed solution general in classical RL? And so here, my errors, I can control it compared to before, because this is only error due to estimation error. So when n increases to infinity, my estimate kernel tends to the right one, and I can control this error in practice. And so once I get this, I would like to count the number of samples I need to converge to this solution. So like it's well known in classical reinforcement learning that, for example, the sample complexity is about, it's proportional to 1 divided by 1 minus gamma to the power 3, which actually is very big. And this is Minimax optimal bound, and this is super big in practice, because when you're a practitioner, you pick gamma very close to 1, as you can see. So that's a very big quantity. So I would like to find formulation with like, which have like lower sample complexity in general to classical reinforcement learning. And because in classical RL, you have Minimax bound, and you know it's impossible to get better sample complexity without any assumption. And so yeah, that's the problem I want to tackle. And about robust MDPs, so I was saying, for example, that I'm trying to find the best policy in practice, but at each step, I am playing again an adversary. We just pick randomly the worst kernel here at each step. So, for example, you're playing tennis, and like you have the worst condition at every step with some probabilities which are like bounded because you need a simple problem. And so basically, here it's not, you're not just trying to find the best policy, but the best policy, again, an adversary will pick the condition kernel at every step. And so I need to assume some assumption on the transition probability that the adversary can pick. And for example, here, I assume so-called rectangularity, SR rectangularity, which is just that my set given S and A, the perturbation is independent given S and A. And I need this assumption mathematically to get solution. And so my adversary can pick transition kernel, which is bounded against the so-called nominal kernel you train on, so pi 0, which is so-called nominal. So like your adversary pick kernel, which is into the simplex, and with bounded perturbation controlled by the radius of the ball sigma. So this is so-called SR rectangular assumption. And you can have the same with so-called S rectangular, which is the same, but you only assume independence of the states of your perturbation here. And we still have a simplex constraint and bounded perturbation. And to what I'm doing in robust reinforcement learning is quite simple. Now I'm not looking for the best policy, but the best policy under the worst kernel in this uncertainty set view here of the Q function. So I'm trying to approximate this purple quantity here, so, which is called robust Q function, parameterized by sigma, which is the radius. And was it possible to approximate this very difficult math problem in practice? We are quite lucky, like, because as in classical RL, we have contraction of so-called robust Bellman operator, which is also a gamma contraction. So basically, I'm just trying to iterate this operator and approximate it in practice to have a chance to converge to this so-called robust Q function. So as in classical RL, I will just try to approximate this operator plus this min under the kernel. So yeah, it's a slightly different problem, I agree, because now Q star is not the best target to try to find, but I will try to learn how many data I need to approximate this quantity. So yeah, this is sequentially interesting, so that's fine. And like in the paper I'm presenting, like before, like the sample complexity was very high, and my first work was to say that for small radius, so for small perturbation, the sample complexity is upper bounded by the same quantity as in classical RL. So here, basically, I have just a result saying that robust MDPs with small perturbation are as simple as classical reinforcement learning. And for a bigger radius, I don't have a slightly bigger sample complexity, but it's due to technical problems, and I will explain a bit after. So I reduce the sample complexity here from previous work. But the main takeaway is not this message, because like recently I continue to work on this subject with Leishu at Caltech, and actually I improved a lot the sample complexity. So here I'm plotting different things. So in blue, you have standard robust reinforcement, classical RL blue line, which is proportional to 1 minus gamma to the power 3. In purple, you have the work I'm just presenting you here. And actually, I realized something from experiments that the variability of the system can be bounded in robust reinforcement learning. Actually, the intuition is a bit strange, but like I'm trying to find like solutions which are robust to variation. And so the variance of my Q function, the variance of my system is decreasing when I increase sigma. And at some point, theoretically, and also in practice, I can bound the variance of this Q function, of this value function, and it reduces proportional to 1 minus sigma, which is the radius. So there is a breaking point here in 1 minus gamma, and suddenly you can reduce the sample complexity of robust reinforcement learning. So you can maybe think about, for example, regression. So in classical regression, you have only few samples, and so you would like to learn a good estimate of your parameters. So what are you doing in practice? People which are statisticians, they just regularize with, I don't know, L2 penalization, for example. And here, like my minimum problem of the kernel, you can think as a regularization of the solution. So you have less variability in the solution, and you need less sample to have to converge to a solution. But you are not converging to the original one. So, just insist on this point. And so for S rectangular assumption, you have the same behavior in practice. So yeah, the intuition is you can bound so-called span seminorm, but whatever. Think about variability of your system. And like I bound the variability of the value function by 1 minus about nice maximum of 1 minus gamma and sigma. And that's why I can achieve lower sample complexity than in classical reinforcement learning. So, and this leads to this kind of sample complexity afterwards. But why is I think this is interesting, maybe also in practice, and not only from a theoretical point of view, is because, for example, in classical reinforcement learning, your problem is not constrained, so you are looking for very like policy which could be lots of variation. And here, I'm just saying that I'm trying to constrain my problem to simple solution with less variability, and maybe I have a chance to converge faster to the solution because the variability of my solution is slower. So, but here I'm only like tackling the problem with some definition of the perturbation using LP norms, but I'm trying to do for F divergence definitions also of my perturbation using probabilities. And this was only for generative models. So now there are also one result in a nice setting, which have the same behavior than I'm presenting you. And so I would like, or like in practice, maybe it could help to design more sample efficient algorithm. You are not tackling the same problem. You're not like targeting the same Q function, which is not, this is a robust one. But imagine that for just limited amount of data, it could be better than the classical one. And my question is, can we like converge faster to a solution which is not too bad in practice? And so, for example, I'll give you here an intuition. So I brought one classical RL algorithm and one robust one. So if you have like plenty of steps at the end, I agree that classical RL would be better than robust reinforcement learning. But if your solution is not too bad and you converge faster to it for like limited amount of data, maybe you could get better solution in practice. And I did some experiments on a benchmark, only using, for example, 1 billion steps. For example, for this kind of task, you need like between 3 and 5 billion steps to get like very nice state-of-the-art performances. But for limiting budget of data, maybe you have a chance to converge faster to a solution because you have less variability in your system. And so it could maybe lead to better solution with few data. So maybe that could be an application of this kind of framework. And so yeah, as I said, robust reinforcement learning allows to learn like solution which generalize better to a solution, but it could may also allow to learn faster in some cases, in some regime reinforcement learning. So yeah, you have simpler solution and you learn it faster compared to classical RL. But you have a trade-off, of course, with performances, because if you like regularize too much or robustify too much, there is always a trade-off between the generalization and performances. So it depends on what you want to do. If you want to be the best, for example, I am playing chess, of course, you will not use these kind of things. But if you want to do like, I don't know, for reinforcement learning for robotics, to be like robust on some model-based specification in real life, it could be maybe interesting. And so, yeah, you have always a trade-off, and I need to generalize my results towards a divergence, for example. And also, if you want to test and try new algorithm in practice and to see if they are sample efficient or to test their robustness, we also implement with some colleagues benchmark where you're trying to like, if you want to like looking at your new robust reinforcement learning algorithm and to see if they perform well on some classical tasks. So yeah, feel free to trying to delve into the subject, and if you have some ideas to create new robust reinforcement learning algorithm for the community, that could be useful not only for robust purposes, but also for classical RL with few data on some very like environment with lots of variation, it could be also maybe interesting. So here, like I also said that really, my results are only for balls which are defined using norms and not a divergence. And so that's also a drawback, and I'm currently trying to generalize all this result to more general class of distance between probabilities. And I think that's an interesting theoretical way of research. Thank you for your attention.
I have time for several questions.
Thank you for the talk and very cool results. My question is, I missed a little bit of when, you know, your sigma term that, like you said, large enough sigma allows you to be like sample efficient.
Yeah.
And like at what point do you actually get that?
So actually, it's a very characteristic like quantity in reinforcement learning, which is 1 minus gamma. And for like 1 minus gamma, you have a breaking point here about the sample complexity. So before, like, it's like really related to classical RL because you are not really robust and you have the same sample complexity. And from a theoretical point of view, what I observe is I can bound like the variability of my value function by the maximum of 1 minus gamma and sigma. So as long as like sigma is bigger than 1 minus gamma, I can like, in a sense, reduce the variance in my bound using this kind of tight control of the spans and amount of my system, which is, you can think of variance using, I don't know, you're doing Bernstein inequality for concentration, and it's related to this span, and so you can control the variance of your system using this information. This is only for robust reinforcement learning and not for classical.
And this radius is the difference between the value function or the transition kernel?
Sigma is defined like how big my adversary can pick transition kernel. So here, for example, like pi is centered on pi 0, which is the environment you are training on. This is also a nominal kernel. And my adversary can pick any kernel which belongs to this ball centered on pi 0. And the bigger sigma is, the more robust you are. But at some point, if you are too robust, the performance can also decrease in practice. So really, I'm not saying this is better than classical RL, but it allows to like generalize solution with this small perturbation.
Thank you.
Would it make sense to start with a large sigma and decrease it gradually to first achieve high convergence rate or fast convergence rate and then improve your solution?
Yes, that's a very good question. Actually, I'm trying to do is this in practice to see if like robust formulation at the beginning, maybe you try to converge at the beginning to a robust formulation because you need like less sample to convert to a fair solution. And then you try to reduce sigma to increase performances. And yeah, currently I'm trying to do this in practice for one paper to see if it's like kind of exploration in a sense to converge faster at the beginning, but you try to increase performances at the end. And yeah, I'm trying to do this. But from a theoretical point of view, it's quite difficult to analyze this kind of scheme. But yeah, in practice, maybe it could lead, I don't know. I'm trying currently to algorithm to improve, I don't know, sample efficiency at the beginning, especially.
Thank you.
Thank you for the talk. Actually, my question is a little bit related with, and the idea is to do some kind of pre-training, but then allow for some additional training whenever you get to the specific task.
Yeah.
Because, you know, when I play tennis, I don't play tennis. If I played tennis, you know, I wouldn't regularize. I'd give it my all. And then if I have to play ping pong, then, you know, I'd start learning again.
Yeah.
But maybe the way to do it is you have some regularized pre-training, and then you do some training on top of that that's more specialized? Or is it better to only do specialized training without any regularization, but then allow yourself to do some more custom learning?
That's also a very good question. So people in computer science, deep reinforcement learning, basically what they are doing, they try to do domain randomization. So they try to sample from many sample, which is close to the ball, and they learn on all these sample. It's like I'm playing tennis against many people, and as I able to play against many people, and maybe I can generalize. Here, it's a bit different because I assume I can only sample from one guy. So if you play tennis, you just train against me like plenty of times, and then you try to generalize to the people. So that's another question. Here, my problem is a bit more restrictive because I assume I can only sample from pi 0. But I also tried on another article to like combine both computer science ideas and kind of a pessimistic estimate of the value function both to see if it's generalized well. And yeah, so the answer is I can maybe also a bit. If you only trying to do kind of robust reinforcement learning and trying to learn only on pi 0, the performance are like not as better as if you learn about many people, like many samples from the ball. So in practice, if you just try to implement my methods and compare to more computer science guys doing the domain randomization, it works better with domain randomization, these kind of things. I agree. But if you combine this kind of ideas from theory and also sample, and you allow to sample from all the ball, then it works better. So yeah, the answer is you can combine both ideas to get better results.
Okay, cool. Fantastic. Thank you.
Okay, but we're out of time, so if you have other questions, please contact the author. So let's thank Pierre again. Okay, so the next talk is optimistic regret bounds for online learning and adversarial Markov decision processes, and the talk will begin by Sangbin.
Good afternoon. My name is Sangbin Moon. I'm a PhD student from Purdue University. And today I would like to share my work with my advisor, Professor Abolfazl Hashemi. So this is the outline of today's presentation. I will start from the motivating the problem of time-varying cost functions, and then I'm going to go on to the problem of adversarial Markov decision process, which captures that time-varying cost function, and also talk about some online learning approaches to solving AMDP and their regret bounds, and then go on to our method called ORAPS OPIX, and also show some regret bounds to that. And then I would extend the algorithm to more general settings, and then conclude the talk with experiments that shows the efficacy of what I've shown in the theoretical guarantee. So time-varying cost functions are very it's easily found in real world scenarios. For example, first, energy efficient drone navigation. In this case, the weather condition can change over time and it can incur different costs to the driver of the drone. And also in the stochastic inventory control problem, the changing economic conditions does that. And in the problem of hierarchical or multi-agent problems, the other policies or the parent policies are evolving over time, and they also incur changing cost functions. And adversarial MDP is one of the framework to understand this time-varying cost function. So essentially, it is same as MDP, and it's a stochastic process where there's an environment and agent, they interact with each other based on the most recent feedback they got. But the key difference in adversarial MDP is that the cost function, as you can see, is time dependent and it can change over time. And more specifically, it's defined as a tuple of finite state space X, finite action space A, and probabilistic transition function P, and the number of layers L, and finally the sequence of time-varying cost functions CT. And more specifically, we consider loop-free episodic AMDP, or if you're more familiar, it's loop-free stochastic shortest path. And specifically also, it's where the state space is partitioned into non-overlapping and ordered layers from X0 to XL. And there are two feedback schemes here. One is full information. It's where the learner observes the entire cost function after the episode T. And in bandit information feedback setting, the learner only gets to observe the cost for the state and action pair that it actually suffered from. And there are two key concepts that I would first clarify. One is occupancy measure. It quantifies the joint probability of visiting a state X and the probability of choosing action A in that state. And essentially, by optimizing the occupancy measure, it automatically is equivalent to optimizing the policy because of the second equation. And regret is the quantity that measures the difference between the cost suffered by the agent's policy as opposed to the cost suffered by the best policy in hindsight. And our objective in online learning in AMDP is to minimize that regret. And one of the approaches to solve this is OREPS from 2013, and it minimizes regret by online linear optimization using mirror descent with KL divergence, and the equation is like this. It solves the problem in two steps, as it is a constrained optimization problem. It first solves the unconstrained version, and then projecting onto the probability simplex. And that results in this kind of exponential update form. And these are traditional regret bounds that are established for AMDP problem. And most notably, you can see that these regret bounds are sublinear with respect to the horizon T, which means that if you divide by T, then the average regret over time will go to 0. However, it can be too pessimistic in some sense because it doesn't assume anything about the changing cost function, but in your world, you might have some idea of what the structure of the time-varying cost function can be, and you can distill that idea or knowledge about it to learning of the optimal policy. So this is the big picture of our method. So there's an environment that gives time-varying bandit feedback of the costs. But here we assume that we have some access to our cost predictor based on our knowledge about the structure of the time-varying cost function. And using that MT, we construct the cost estimator. And then using that, we solve the online linear optimization problem, to update the occupancy measure, and it implicitly means policy, and according to that policy, plays an action again. In more detail, this is the form of the new cost estimator that we suggest, which contains both the cost predictor part and implicit exploration part. And yeah, notably, this specific form of cost estimator allows us to bound the variance, and as well, the cost estimator also enjoys variance reduction property. And finally, we adopt single projection method from Jelani et al. And solve this kind of constraint optimization using the OREPS solutions that we already have. And this is the main result, one of the main results. And it's the regret bound in the bandit feedback setting and also in expectation. And under known dynamic setting, this OREPS OPIX algorithm satisfies this kind of regret bound, where optimistic cost predictor satisfies that the optimistic cost predictor always underestimates the true cost. And there are two things to note here. One is that our bound is also sublinear, and also it's not just pessimistically dependent on the order of t, but instead it has a factor that is related to the prediction power of our predictor. So as better predictor we have more tighter bound and lower regret. But also in the worst case, if we don't have any idea about what the cost will be, in that case also it's sublinear to t, so it's still sublinear. And on top of this expected version of the regret bound, we also have similar sublinear optimistic regret bounds for high probability guarantees and as well as full information setting. Now I would like to extend to more general setting because setting of anytime version, because the learning rate eta that satisfies that regret bound that I just showed you is based on the knowledge of unknown values such as t or ct. And therefore we extend this algorithm to anytime version by utilizing doubling trick. Doubling trick basically is starting from a large enough eta 0, it reduces the learning rate by half every phase, and the phase is defined by this inequality here. And it uses the accumulated quantity that's accumulated over from the beginning of the state, from the beginning of the phase to the current time step. And because of the introduction of new cost estimator, handling of this is non-trivial. And also, we extend to unknown transition setting because in more general setting, the dynamics of AMDP is not revealed to the learner. And to deal with this problem, we keep a confidence set, which is a small ball of size epsilon over around the count-based empirical transition probability. And by keeping that, we can get the upper confidence bound. And instead of the occupancy measure, we put in the upper confidence bound in the cost estimator to deal with the unknown transition setting. And for both the anytime setting and unknown transition setting, we also established analogous sublinear optimistic regret bounds. And finally, it's experiment. This experiment is on the energy efficient drone navigation task. So the agent navigates a drone to the goal state by moving to its neighboring cells. And the cost is 1 for the cell that has a wind inside, and that's the maximum cost, and epsilon everywhere else. Wind location randomly changes every 1,000 episodes. That's basically the change in cost function here. And when drone reaches the target, it remains in the terminal state for the remainder of the episode with the cost of 0. And these are the algorithms that I compare with in the experiment. First is the original form of OREP's algorithm as introduced back in 2013. And second is OREP's IX with implicit exploration parameter gamma greater than 0. And our algorithm, OREP's OPIX, with different kinds of predictors. First predictor is the latest predictor, and it stores the bandit cost feedback from the last visit to the state and action pair. And otherwise, it's filled with 0 as default. And it resets all the values to 0 every 1,000 episodes, so that that's exactly when the wind location changes. And that's because we have to keep the optimistic prediction assumption. And second predictor is more reset predictor, which resets every 500 episodes. So it basically resets too early. And because of that, it incurs higher prediction error. The last reset one resets every 2,000 episodes, so it resets too late. And for that latter 1,000 episodes, it has the risk of overestimating the cost, which violates the optimistic prediction assumption. Finally, perfect predictor, we assume that we have access to the true cost function of the next episode. And this graph shows the average regret of different algorithms. First to note is that the blue line, which is the OREP's algorithm as it is in the original form, diverges without implicit exploration. And this is partly due to the exponential update that converges really fast to the current cost function. And when it does, it reaches to the occupancy measure of 0 for some states and actions because of the precision of the floating point. And when that happens, it never visits that state and action pair again and results in this divergence. And also, if you look at the green line, which is OREP's OPIX algorithm, and that improves both convergence and variance over the OREP's IX in orange line. And this figure shows the prediction error of different predictors. And as you can see, the positive error of the green line shows that the latest predictor is in fact optimistic. And the value of the latest predictor is always less than the true cost. And these shows the performance of OREP's OPIX with different kinds of predictors. And what you can observe here is that the latest predictors based on inaccurate information, which is purple and brown, which is more reset and less reset predictors, they perform as well as the one with accurate information, which is the green line. And this confirms that the less reset predictor in brown is actually overestimating for some of the states and actions. And even though it overestimates and violates the optimistic prediction assumption, as you saw before, it still does empirically very well. So I would say that optimistic prediction assumption is more for the mathematical convenience than what it truly implies in this setting. And as a summary, we introduced a new algorithm that uses a new form of cost estimator and also enjoys the bounded variance property. And we achieve sublinear and optimistic regret bounds for bandit feedback, full information feedback setting, and also in expectation with high probability. And also we extend the algorithm and those bounds to the anytime version and unknown transition setting. And those faster convergence and reduced variance that we guaranteed are also confirmed by numerical experiments. Possible future directions could include further improving the sublinear regrets to the square root of t so that they match the pessimistic results in the worst case. And also developing accurate cost predictor because we didn't propose any specific form of cost predictor here. So it could be another direction. Also, even involving with the adversarial ones using some game theoretical approaches could be viable. And if you have interest, please check our QR code, which leads to our paper. And thank you.
Okay, we have again time for several questions.
Right, thanks for the talk. Can this method be applied to both continuous and discrete state action space, or is it only for discrete?
It's only for discrete state actions. Yes.
Any idea on how to extend that to continuous?
I think as long as we deal with occupancy measure, I think it would be difficult, but we can always extend this idea of optimistic predictor to directly optimizing the policy. Maybe then the method itself could be viable. Okay.
Thanks.
Any other questions? I'll ask a question. So what is it that made it difficult? So the previous methods had all regret, which was square root of t, but yours is t to the 2/3. So what was it that made it more difficult to analyze or to achieve the square root of t?
Oh, yes. That was partly due to this exploration term gamma. However, without that gamma, we couldn't achieve high probability guarantees. So it's quite essential in bounding the variance. So yeah, that is kind of problematic, but there should be some way to reduce the bound to square root of t, but I don't have it right now.
If there are no more questions, let's thank the speaker again. Okay, so the next talk is group fairness in predict and optimize settings for Restless Bandits, and the speaker is Niclas.
Thanks for the introduction. Yes, my name is Niclas, and this is joint work with Shresth, Yunfan, Sanket, Aparna, and Milind. And Shresth and Yunfan are really the drivers of this work. Unfortunately, both of them have visa issues, which is why I will now present our work, Group Fairness in Predict and Optimize Settings for Restless Bandits. And I want to start by giving a bit of context and by unpacking the quite long and wealthy, rich title, I would say. So I will first talk briefly what Restless Bandits are, then talk a bit about group fairness, and then predict and optimize settings, and then actually talk about what we do and our experimental results. So Restless Bandits, in Restless Bandits, we assume that each arm is modeled by a Markov decision process. And in this paper, we purely focus on decision processes with two states, where we can think of one state as a good state and one state as a bad state. And the good state gives us a reward of 1, and the bad state gives us a reward of 0. And then we can, in each time step, decide for each of the arms whether we want to apply action 0, which corresponds to not pulling the arm, or action 1, which corresponds to pulling the arm. And like classically MVP style, we have different transition matrices based on which action we choose. And the objectives in these multi-arm bandits problems is now to maximize the arms in the good state by pulling k arms in each time steps. And the classic solution, which we also employ in this work, is the so-called Whittle index policy, which computes for each arm in each state what you can think of as the expected benefit of pulling the arm. So some number that is the expected reward gain. And what we do then is we just sort the arms and pull the k arms with the highest Whittle index. Now, why does group fairness come into play here? Restless multi-arm bandits are increasingly used for high-stakes decision-making, for instance, cellular networks, anti-poaching, and public health. I will mostly be talking in this paper about the public health application. So, for instance, here you can think of each arm as being a person, so being a beneficiary to a public health program. And then we have like one NGO that we partner with in this context, and that kind of their concerns also gave rise to this project. For instance, they want non-discrimination based on sensitive attributes and prioritization of marginalized groups. And one thing that is particularly important to them is that they don't want that by allocating resources, the gap between different groups just gets wider and wider. So just to give one simple example here, you can think of, we have like two groups, marginalized and non-marginalized. For marginalized groups, we say they get a 0.2 reward if we don't do anything. If we give them a resource, they get 0.35. And for the non-marginalized groups, it's 0.5. If we give something to them, then they get 0.7. So a purely utilitarian policy, which just wants to maximize reward, would give the resource to the non-marginalized group because it would give us some 0.9. But that's exactly what we don't want, because we want that the gap between the different groups doesn't get larger but smaller due to the allocation of the resources. And that's where like group fairness notions such as Minimax fairness and Nash welfare come into play. Now we tackle this problem of group fairness, restless, multi-arms bandits in the so-called predict and optimize setting. So the idea is that we are given for each arm some features, and we are given like an offline data set of historic transitions. So the first step that we need to do is we need to have, from the arm features, we need to predict their transition probabilities. So we will train a neural network that, based on arm's features, will output the estimated transition probabilities of this arm. And there's a second step of, okay, once we have these transition probabilities figured out, we can model each arm, and then we can apply this like Whittle index policy to actually perform the optimization and the decision making. So we have these two steps, predict and then optimize. And then there are two different ways that we can solve this problem. The first one is what we refer to as the two-stage approach. So to do both of this separately, first do the learning, then the learning is done, and then do the optimization. Unfortunately, it turns out that this is not really a good idea, because the predictive accuracy in the learning part, you just want to usually optimize some form of predictive accuracy. But this does not necessarily correspond to the decision quality in the end. So then there are regularly cases where we have very good estimates of transition probabilities, but we made kind of errors which come into play very unfortunately in the downstream decision quality. So we want to not do these two parts separately, and that's where the idea of decision-focused learning comes into play, where we want to put all of this together in one fully differentiatable pipeline. So we do the data, then we have the neural network prediction and then the optimization, which in the end results in like this decision quality, which in our case is the fairness objective that we want to maximize. And we backpropagate through the whole pipeline, and thereby also take into account the downstream decision quality of our policy when learning the transition probabilities. So the status quo is that like this decision-focused learning on RMAPs, this has already been done quite a bit. In particular, like in our application context, we have one policy right now deployed, which does this RMAP in a DFL style. There's also one other paper that does group fairness on RMAPs, but in a two-stage setting. So they assume that transition probabilities are given and purely focus like on this second problem of given transition probabilities, how do we do the optimization in a group fair way? Which is in particular non-differentiatable, so that kind of didn't really work right outside of the box for the DFL pipeline. And there are also various works on individual fairness in the RMAP context, where we just focus on, okay, each arm is fairly treated, which oftentimes mean they are pulled proportional to the reward that they generate, for instance, if they get allocated a resource. So our contributions here is now we developed the first decision-focused learning pipeline for fairness in RMAPs. In particular, this required coming up with a budget allocation method, about which I will talk quite a bit. And the nice part is that this whole pipeline is more or less exchangeable. So the fairness objective in the end, as long as it's differentiatable, you can just plug in your own fairness metric of choice. So there's a little bit of notation here, but I hope it's not too ugly. So we assume that we have given some set of groups. Small g is just like one group, and ng is the number of people in a group, and sg is the state vector. So 0, 1 vector is for all the agents in the group. And then the key idea is like this value functions of groups. So it's just a classic Bellman equation here. So what this means is we assume, so we will have like a budget allocation on groups. So bj, bg is the budget allocated to group G that will be fixed, or our like, as part of our algorithm, we will figure out these budget allocations for each group. So let's say group 1, for instance, gets here a budget of 5. And then we assume this is just like the current states, and then this just describes the expected reward that we gain from this group if we assume that we can allocate BG resources to them under This is now solved with the Whittle index policy. And now we use this group fairness. We used mainly two different models to solve this. So the first one is this now here comes this value function comes into play again. The first one is the Nash welfare, where we simply multiply the different value functions of the different groups. So we want to maximize the product of the values generated by the different groups. Here, what is important is the value is the value after we allocate the resource. So this is all like post allocation. So we want to allocate the resources such that the reward generated by the different groups, if you multiply it together, it's maximized. And the second one is the maximum reward, where we just care about maximizing the minimum reward. So we care about the group that has the least reward generated, and we want to maximize this minimum reward and choose the budget allocation accordingly. But yeah, as mentioned, kind of the whole thing works also with different fairness notions. So to now come to our pipeline, we have a couple of steps in there. First of all, we start with these ARM features. Then from the features, we need to learn the transition probabilities. Then given the transition probabilities, we compute the Whittle index for each ARM. Then given the Whittle indices, we find a budget allocation, so some form of allocation of the total budget K to the different groups. This was this PJs, which I was talking about. And then given these budgets for each group, then we can just simply apply a top K rank algorithm. So we just say, okay, if we have three resources allocated to this group, we just pull the three arms out of this group that have the highest Whittle index. By the way, I should have said this earlier, but groups are disjoint. And now the idea is that we want to differentiate through this whole pipeline. So our metric that we in the end care about is this decision quality as measured by the fairness objective. So for instance, the product of the values, if we are in this, of the value functions, if we are in this Nash welfare setting. And we really want to backpropagate through the whole pipeline, and thereby also update the transition probabilities, taking into account the decision quality. And what we will do in our algorithm is we perform alternating updates of the transition probabilities and the budget allocation. These are two things that we need to figure out. We need to figure out for each arm how they transition, and we need to figure out for each group how many resources we want to give to the group. And we will update them in alternating fashion. And for this, we need to be able to differentiate with respect to the transition probabilities and with respect to the group allocations to perform these respective updates. I very briefly want to talk about kind of how we split up the gradients and roughly speaking what we do there. So to update the group budgets, we split the gradient as follows. The first one is we want to differentiate the fairness objective, so the decision quality with respect to the Whittle index policy, and then the Whittle index policy with respect to the budget allocated to the group. And to compute the fairness objective, the fairness objective differentiated by the Whittle index policy, we just split it up again into two steps. The first one being these group values that I featured earlier. So we differentiate the fairness objective with respect to the group values. For the Nash welfare, that's easy because it's a product of different value functions. For the maximum reward, it's a bit more tricky because there we have a minimum, but we just use the differentiatable Hölder mean to approximate the min, and then again it becomes differentiatable. And the second step is we want to differentiate the group values with respect to the Whittle index policy, and for this we use some gradient policy theorem, which basically tells us that we can, given the Whittle indices, we can compute this policy group values using importance sampling, which turns out to be differentiatable unbiased. So that's how we can also figure out the second part and thereby drive at this term. And then the second part of this update function is that we want to differentiate the Whittle index policy with respect to the group budget, so the number of arms that we can pull within this group. And for this, we can formulate this top K selection problem as entropic optimal transfer problem, and again, compute some approximate gradients. And the nice part here is that you can actually show that at least for the fairness objectives that we consider here, that the optimization landscape is well behaved, in a sense that the continuous functions extend the fairness notions are concave in the group budget values, which kind of gives us hope that the local minima that we find might actually be also global minima. And that gives us the way how we can update the budget allocations. And the other question is how we update the transition probabilities. For this, we use a neural network, so to learn them. So we want to ultimately update the weights of this neural network. And here we can split up the procedure again. This part I've already told you kind of how you can differentiate the fairness objective with the Whittle index policy. And this part is known from prior work. So here we differentiate the Whittle index policy by the Whittle index, then the transition probability, and then by the network weights. So yeah, that was already known how to do it. Now coming to the experiments, we have a bunch of baselines. The most important one here is this, or I think the most two important ones is this Kilian et al. Paper, which does group fairness, but does it in this two-stage approach, where you first just learn, then stop the learning, and then afterwards do the decisions, but now do the decisions also in a way that respects group fairness. So that's one interesting baseline. The other interesting baseline is like this DF no fair, which is a DFL approach where we combine these two, but we don't care about fairness, so we just want to maximize some utility. And then this DF learn D is the pipeline that I just explained, so kind of the pipeline that we propose here. And now this is just some results from a synthetic domain where we sample transition probabilities somewhat randomly under the condition that we have positive action effects. I want you to focus here just on this left part. So here we see the maximum Nash-Bell fair metric, and we have just two groups. And here we see the value of the fairness objective. And what we see is that this two-stage approach here performs the worst, and even worse than this DFL approach with no fairness. So that actually implies, or what this tells us is, okay, doing this decision-focused learning in this context actually helps you quite a bit, because even if we don't care about fairness, we still actually perform better with respect to fairness, because the Kilian et al. Two-stage version, yeah, just makes a lot of suboptimal decisions. And then we see roughly what we want to see here is that, okay, if we don't care about fairness in the DFL one, then we get, I don't know, something like 0.5 normalized fairness value, but our, like with our pipeline, we get substantially better results. And the other nice takeaway here is that you can actually do this group fairness while only having a marginal utility loss. So you see the blue one is normalized here to be 100%. So if we do decision-focused learning without fairness, then we get 100% of utility. And if we move to the fairness and kind of impose the national welfare group fairness, then we still are, I think, at 95% of the utility. So we only lose very little, but distribute the utility in a much nicer way. Yeah, you can also look at how much the budget changes over time. So the group budgets that we allocate, here we see that our pipeline, which is in brown, is much more, or much less erratic than the other methods. So we nicely continuously update the budget allocations. Yeah, whereas the other ones are less stable and kind of more in oscillating fashions. And now I want to very briefly talk about like the initial application domain that I mentioned. So this is from a public health program in India where they deploy, or it's a program where you can enroll and then you get automated voice messages about health information for young mothers. And the hope is that by improving the health literacy of mothers, that actually leads to better health outcomes for the mothers and the babies. One problem that they face, though, is they have 25,000 people enrolling every month, and they have some limited number of service or of health workers which can assist them in some way by giving them details in the program about the program, how to enroll, how to continuously listen. So it's like a limited resource allocation problem. And they also have groups that they actually want to respect or that they somewhat care about. And here the groups are defined by risk scores. So each beneficiary can collect a number of points, one for being low income, one for being low education, one for being a phone owner. And then you sum up this number of points and then you arrive at the risk score. So 3 means you are at very high risk. So you are kind of from a very poor background. 0 means that you are kind of at lower risk and generally should have better health knowledge. And now we apply also these baselines here, and this is now the maxi-min reward, where we care about the minimum group, and we again see that our pipeline performs best. We have again that the DFL no fairness one actually performs better than the two-stage, and the utility loss again is somewhat marginal. And just as a very last slide, we also looked at the budget allocations. Group D and C here are the high-risk group. So if we compare now, if we don't care about fairness, then these high-risk group get only a small chunk of the budget. Whereas if we start caring about fairness and impose maximum reward, then these like two most marginalized groups get, I think almost all a very large chunk of the budget, which was also something that the NGO really like to see. And with this, I want to thank you, and I'm happy to take questions.
We have again time for several questions.
Hello, thank you for the presentation. This is a non-technical question, but what do you think it would take for your method to physically be implemented by like the runners of Armman?
Yeah, that's a very good question. Let's say we are in discussions of whether they want to implement it or not. I think currently the biggest roadblock actually to implementing it is that they are not sure how to define the risk groups. And whether they actually want to do it, and whether kind of this also is as a political mandate to say we actually want to change the allocations in some way, because it's always like a longer regulatory process, and we have a status quo that kind of works, and then changing the status quo always, I think, faces some resistance. But I think from a technical perspective, we are kind of ready, and I think they like the initial results that they saw.
Thank you. It was a very good presentation. Can you discuss more on the deployment of your approach and the baselines on the actual population targeted by the NGO?
Yeah, so the like these experiments here are actually from like on the target population. So here we just looked at all like 44,000 mothers that were enrolled in, or I think that enrolled into the program in January 2022. That's also what they do. They only look naturally because people kind of enter the program and then leave the program again. So you have to take a snapshot of like, okay, these are the people that are here in 1 month. And then they exactly make like these allocation decisions of like, okay, which of these people should get a support. You can think of it like the support resource, or like something in addition to boost their engagement in like this health program. So that's actually the test set that also happens, and like the blue algorithm is the one that is currently implemented. So these are really like the decisions made by the blue algorithm are really the decisions that were made in the real world, I think in like January 2022. And yeah, we see here that if we assumed, or if we focus on this 1 month, then we really had like a better fairness quality at a somewhat lowish utility loss.
Thanks for your presentation. Can you go back on like what is the optimization problem that you're solving, and how do you solve it? Maybe I didn't catch that.
The optimization problem is this, I mean, consists out of 2 parts. So like these are the fairness objectives that we want to maximize in the end. So we have like these different value functions for the different groups. And for instance, like in the Max-Nash welfare, we want to, I mean, we want to, there are 2 decisions that we can make. So two things that we can modify. The first one being how much budget we allocate to the different groups. That's like the first decision that we need to make. And then assuming that we allocated the budgets, and the question is which of the arms in each group do we pull? So which of the, in the context of the program, is which of the beneficiaries from each of these groups gets an additional resource. And we want to make these decisions as to maximize this function, for instance, if we do Max-Nash welfare.
We also have a random function so that adding them together, or you just have these 2 separate options?
There was just 2 separate ones. So like we, I think in the results that I showed was like for this maximum rewards. So these are just like to showcase that the whole thing works for 2 different fairness notions. This one here is a bit like the conceptual difference here is the Max-Nash welfare. If you do the product, then you usually try to balance off fairness and efficiency. So you want to have the rewards to be somewhat balanced, but if it's clear that like an additional resource doesn't really increase much, then the product also doesn't really increase much. So you balance equity with efficiency in some way. Whereas this maximum reward really just focuses on the worst of group. So even if it's very inefficient to give them an additional resource, the maximum reward will give them an additional resource if they are still the lowest group. So it's like fundamentally 2 different philosophies to group fairness.
Okay, so it seems like it's well known that when you improve fairness metric, then you will decrease their utility, right? So
yes,
let's say if you only maximize their welfare function, then I don't see why like the utility still stay the same. Like, is there any intuition that explain why your accuracy is still high?
So I mean, necessarily if you go with this instead of, I mean, the baseline is just a sum. And if you do one of those, then you will end up worse with regards to the sum. I think why in practice it seems to be not as much of a difference. So in practice it seems like you have relatively many choices in how you can allocate, which all leads to similar sum welfare values. So it just looks like there's a lot of flexibility in how you can make the decisions without like influencing the sum too much. Thank you.
Okay, let's thank the speaker again and we'll move on to the last presentation, which is called Recursively Constrained Partial Observable Markov Decision Processes. And the speaker is Heng.
Thank you. I'm Heng Ho, and I'm working at University of Colorado Boulder, and this joint work with CU Boulder and NASA Jet Propulsion Lab. So we work a lot in robotics, and we were trying to do formulate our problem as a constrained partially observable Markov decision process, which is constrained POM-BP. And we were realizing that there were some really weird behaviors that come out of the optimal policies of constrained POM-BPs, which led us to do this work and define this new problem formulation, which we call recursively constrained POM-BPs. So generally, the problem domain that we're interested in is decision-making under uncertainty or sequential decision-making under uncertainty, where we could have robots like autonomous vehicles or exploration robots, healthcare diagnosis and treatment, machine maintenance, or like chatbot monitoring, right? And in a lot of these kind of situations, you have transition uncertainty and also importantly state uncertainty, where you cannot directly know what your state is. So you get only observations, and then you have to make decisions based on that kind of situation. And to zoom in on a kind of a running example scenario, as I said, I'm a roboticist, so this is a robotics example where you have a robot with noisy dynamics, where you take some actions and then you get some noisy next state, and you have uncertainty over the type of traversability of the ground, right? It could be like bad sand or rocks or something like that. And you can classify the traversability if you're close enough with some noisy observations. And the goal is to reach some reward regions, and it could be high reward regions or low reward regions, and you have costs for so-called traversing that terrain or battery life or something like that. And the goal is to also cap your cost, right? You don't want your cost to be too high. So this problem can be formulated as a partially observable Markov decision process, where in this session, we've already heard a lot about MDPs. You have a bunch of states, you have actions, and when you take actions at certain states, you transition stochastically to another state, and you get rewards based on that. But here in a POM-BP, you don't actually know your state exactly. So then you need to actually reason about distributions over states or what possible states you could be in. And that's depicted, that's depicted here, which looks something like a Bayesian network, except I added this belief nodes here, where your states propagate according to the actions that you have and you get rewards, but then you also get observations that you act over, right? So here you maintain a belief distribution over the possible states that you're in. And that's what I mean by planning over belief states, where your policy is not a mapping from states to actions, but it's mapping of distributions of states to actions or belief states to actions. And the goal is to maximize cumulative expected reward. And this is what the POM-BP goal is. And it's been shown that deterministic policies are sufficient for optimality. And it's very nice, and there's a lot of nice algorithms for POM-BPs. But in our case, we don't just have rewards, we also have costs. And you could, in principle, kind of do a scalarized reward, but maybe in some cases you want to separate rewards and costs and give like thresholds for costs, for example. And this is what you can do. You can define similar to reward value function, you can define a cost value function, which is the expected cumulative cost. And you can have a goal that is maximize your cumulative reward while giving a threshold on the cost. And this is the commonly defined as a constraint POM-BP, and that's the objective that people generally use when they have these kinds of problems. Interestingly, it's been shown that policies may require randomization, so you cannot just search over deterministic policies. But people have also designed pretty good algorithms, especially for moderately sized POM-BPs, where you can get optimal policies in finite time. So what we have here is that we have POM-BPs, which are only for scalarized reward functions, deterministic policies, and we have constrained POM-BPs that handle reward objectives and cost constraints, but may require stochastic policies, which is, not necessarily a big deal. So, back to this running example, we can, kind of talk about the evolution of the system. So you can take actions that goes to the left, and you can measure, what kind of terrain it is. So maybe it's not traversable in red, or traversable. You can get observations on that, or you can, maybe directly go to the other region here, and you can do that over and over again, and then we can abstract this as a POM-BP, or very simplified representation as a graph here, and then we can define state rewards for the state action pairs, which gives us expected rewards and expected costs for the belief action pairs. So, and then if we define a constraint like C hat equals 5, we get an optimal policy that says always choose A. Or we run our algorithm, and the algorithm says we get the optimal policy that always choose A. And if you check it, it indeed satisfies the constraint. The expected cumulative reward is 12, and then the expected cumulative cost is 5. Right, which satisfies 5 is less than or equals to 5. But the main thing about our work here is we realized that there were some, if you execute these policies that are optimal according to the constraint POM-BP objective, it has very unintuitive behavior, which we've called the stochastic self-destruction. And I'll go into more details of what that means. So, the optimal policy says always choose A, and let's say we, at B0, we take action A, and we 0.5 for the time, 0.5 probability, we reach B1, right? So now we have a decision to make at B1. We have not taken any, we have cost of C5, but we have not incurred any expected cost, or we've not got any expected reward. So, between A and B, A doesn't seem very desirable to choose, right? Because expected cost is 8 from B1, which is greater than 5. But on the other hand, B seems to be more intuitive. You expect the cost of 5, which is, satisfies the constraint. But the optimal policy says to choose A, right? Which is, a little bit strange when you're trying to deploy something like a robot on Mars, where, you don't really want the policy to purposely violate the cost constraint, right? But if you look at the math of why the constraint POM-BP policy does this, it's because, it's taking the expected cost from B0, which is where you define your constraint. And the expected cost for B0 is, the expected cost from B1, and the sum of that with the expected cost of B2. And if you add it up together, 0.5 times 8 plus 0.5 times 2 is actually 5, which actually satisfies the constraint, right? So according to the math, checks out. But at least intuitively, it's a little bit strange, because what we're seeing here is that the decision at B1 is actually kind of conditioned on what happens at other parts of the space, right? And what we show in this paper is that this actually violates the optimal structure property, where because our constraint is only at B0, so your subproblems depend on each other. Okay, what we're seeing here is that if you compute the expected of B1 for the optimal policy, it's 0.5, like I said, but that is if you are taking action A at B2. But what happens if, in another world, you decided to take action B at B2, is that you will get an expected cost of 5, and taking action A at B1 actually violates the cost constraint, right? So you actually have like, it's kind of like a game you're playing where you need to also know what's going to happen when at other subproblems when you're deciding at the subproblem of B1. And, that itself is not a totally bad thing. CPOM-BPs, violate the standard form of Verma principle of optimality, but you can still find optimal policies for that, right? So not inherently a bad thing, but then you have some issues in terms of the unintuitive policies, and also you get inconsistent solutions, which is to me it's one of the more pathological cases, where if you have this optimal policy and you actually reach B1 or B2 or whichever node you reach, and you do replanning, because in many cases we want to resolve for the policy, right, or decide a new action. The replan policy is not going to take A; it will actually take B, and you will get a cumulative reward of 6 instead of 12, right? So it's almost like the optimal policy that you computed initially lied to you and said that you get 12, but actually you only get 6. And in fact, if you go back a bit, you go to B0, and if you take B action B instead, you would get a expected reward of 10, which is actually higher than if you did the replanning, the whole thing of replanning. So that was a little bit weird because then you get myopic behavior if you do constraint POM-DP planning, right? So what we have here is we have POM-DPs that are only for scalarized reward functions and CPOM-DPs that handle these rewards and costs, but then you could have this kind of unintuitive behavior. And that is rooted in because the constraint is only at the initial belief state, and that violates the Bellman's principle of optimality. So basically what we've done in this work is to kind of attack the root of the problem, which is that the constraint is only at the initial belief state, and define additional constraints recursively from the initial belief state based on this idea of like a cost budget. So what it looks like is at every belief state, we have a new constraint like this, which is how much expected cost has been incurred and how much expected future costs you have, right? So it's kind of like a constraint at every node based on that. And we don't have to do this like, you don't have to always look at the history because we can compute this recursively, where we have the same initial constraints he had for the initial node, and then we compute a recursive constraint based on how much expected cost has been incurred by the agent. And this gives us a new RC POM-DP objective, which is maximizing the expected future rewards and constraining every belief to have this admissible cost budget. And we can define it for up to some k time steps. So the normal C POM-DP objective will be k equals to 0. And here we have any k number of time step up to infinity. And that's what we call an admissible horizon. So what it looks like for a running example is C POM-DPs where we only constrain at the initial belief. But for us, we constrain at every subsequent belief, which I think it seems quite reasonable, where we just add how much cost has been incurred into the constraint. And if you have a larger POM-DP, then you would kind of have constraints as you go along that recursively added to the problem. And at this point you may be thinking, okay, there's a lot of constraints, so how are we going to do anything about this, right? But it turns out that actually adding these constraints for RC POM-DP gives us very nice theoretical properties. Firstly, we showed that the evolution of this augmented belief state, which is the belief state, the normal belief state, and the admissible cost constraint is Markovian. And that means that this is a sufficient statistic to plan for or to decide on for RC POM-DP. Secondly, we also showed that unlike C POM-DPs where you may require stochastic policies, it's sufficient to search in the space of deterministic policies, which kind of like reduces the search space quite a bit. And we can finally also define a Bellman operator for RC POM-DPs that satisfies BPO. And this is quite complicated, but basically it looks almost like the normal MDP or POM-DP Bellman operator, except we have this constraint on the admissible cost. And what it means is that we can repeatedly apply the Bellman operator when you have optimal policy without worrying about whether or not it will become not optimal, right? And that is related to the last point, which is that we showed that this Bellman operator is actually a contraction mapping on the reward value function under suitable initializations, which means that it's a semi-contraction because it's not a full contraction in the usual sense because you have to only under certain initializations it will contract. And that those initializations are when you start a policy that is like super conservative and is already admissible, then you actually contract to the optimal policy. And so these are the theoretical results. And basically what we've done is that we've tackled the root of the problem and defined this constraint at every belief state that allows us to have optimal substructure property for RC POM-DP. And the nice thing about this is that these theoretical results allows us to define a very, very simple algorithm that is almost like a normal POM-DP algorithm, except we just change the Bellman operator to this new Bellman operator. And how it works is a sampling-based search algorithm in which we start from an initial belief state, except we have a pre-processing step. And this pre-processing step is to compute a minimum cost policy because, I said, you need a suitable initialization. So this is basically finding the suitable initialization. And we do a branch and bound over the, rewards and costs by, maintaining upper and lower bounds. And then we can find an optimal policy. And we showed that in our paper that this algorithm is sound, but it's not complete, because we realized that in some cases you need like an infinite number of search in order to show that you are satisfying the constraints. If your constraint, if you know the K admissibility horizon is actually infinite, you may need infinite number of steps. But it's sound and we can find solutions for it. So our evaluation is mainly focused on comparing policies from CPOM-BPs to those of RCPOM-BPs. Don't worry so much about the table because I'll zoom in a little bit more. And we looked at some environments which are common, like POM-BPs and constrained POM-BP problems, except this counterexample running example. And we looked at a few different algorithms that solve constrained POM-BPs. I'm going to zoom in on these two algorithms because CGCP, which is a column generation algorithm, performs generally the best, quite similar to this exponential gradient algorithm. And we also look at what happens when you do CGCP with replanning at each decision point. So what you're looking at here is the expected rewards and costs over these different environments. In blue, we have the CGCP, the CPOM-BP algorithm, and it gets, optimal rewards. But our CPOM-BP algorithm gets lower rewards, but seems generally competitive enough to CPOM-BPs, which kind of shows that our additional constraints, although yes, they are more conservative, they're not like that super conservative in the sense that you can still get decent number of rewards. And interestingly, our average cumulative cost is almost the same as the CPOM-BP algorithm. And that's because adding these additional constraints don't actually change that much the problem, except it actually fixes the stochastic self-destruction property of CPOM-BPs. What you're looking at here is the violation rate, which is the percentage of trials in which you have that kind of behavior where you get violation of the admissible cost budget, or it seems that you don't want to take the action that the CPOM-BP algorithm picks. And over all these environments, you see that this behavior is pretty high for CPOM-BPs, whereas we have no such stochastic self-destruction or unintuitive behavior because there's no violation rate. And we also looked at what happens when you do this closed loop replanning with CPOM-BPs, and we see that over all these environments, when you do closed loop replanning, you basically get like almost half or even worse rewards compared to the CPOM-BP algorithm, the original solution. And in many of the cases, it's even lower than our CPOM-BP algorithm, right? So, and it doesn't even fix the violation of the stochastic self-destruction. So even when you do replanning, you still get like weird behavior. So we think that our CPOM-BPs kind of address a lot of these issues or CPOM-BPs that I've talked about. And going back to this toy example, what we see here is that when you do CPOM-BP algorithm, you get 12 and 5.19 costs, expected costs, but the violation rate is basically half. And that becomes 0 when you do replanning, but you get only 6 expected rewards. But whereas our algorithm, knows that you couldn't have done this going to the left side of action A, but it takes this other action that gives you, a moderately good reward of 10 without any of this violation. So in conclusion, we've looked at what happened to CPOM-BPs when you execute the policies, and we realized that there was some unintuitive behavior that is rooted in the constraint itself. And we've defined a new formulation that satisfies Boehmer's principle of optimality and resolves some of the issues, and surprisingly gets almost pretty competitive rewards to CPOM-BP. And we think this work kind of opens up a lot of new questions, such as what common constraint POM-BP problems exhibit strong cases of such unintuitive behavior. Also, what classes of RC-POM-BPs are decidable or approximable, and better policy representation in algorithms, such as reinforcement learning algorithms for these constraint problems, and extending RC-POM-BPs to other risk measures, because we've only looked at expectation, but we believe that value at risk or conditional value at risk would also have such behavior. And currently, we are also applying RC POM-BPs to space exploration domains with partial observability. With that, thank you for your attention, and happy to answer any questions. And I'll also be at a poster session tomorrow, 7:46. Thank you.
Thank you. Very nice talk and very interesting results. So I just have a clarification question, which I may have missed. So your constraints that you're imposing on the belief states B1, B2, and so on. So aren't these random variables like B1 and B2? So like what form do the constraints actually take?
Right. So they are.
So are these on expectation or like?
Yes. So the constraints are on expectation, but your belief states are, they are. We'll go real quickly. Your belief states are actually like, in our case, we have a finite like state space. So your belief states are like just simplex over the state space, right? So what happens is that when you take an action, you have like a deterministic number of possible belief states that you could be in, right? So it's like an implicit constraint. We don't like constrain everything from the start. But what we're saying is that if you do reach this belief state, what is the constraint that we have? Does that make sense?
Okay. Thank you. Makes sense.
I would like to ask about the theoretical results of the work that you answered the optimality, but what if the constraint in the intermediate step T make the result of the V value over the belief out of the constraint interval, say?
I'm sorry, could you repeat the second part of the?
Like if in the intermediate step of the value iteration, for example, the result of the V value you get is out of the confidence interval of the V allow for the constraint, then can we still get the optimality?
Right. I think I understand what you're asking. So basically because as I mentioned, the result for the theoretical result is based on a suitable initialization. So it's not like we have gamma contraction everywhere. You have to start with a specific value function, right? Or a policy that induces a specific value function. And that suitable initialization is when you basically your policy already satisfies the constraints, right? So then when you do a Bellman update on it, it's almost like you're just doing a normal POM-BP Bellman update that because then you just have to check whether or not you're going to violate the constraint if you took that action, but then you already know that you have a policy that satisfies the constraint. Does that kind of answer your question? We can talk more offline.
Thanks again for the talk. Just maybe like 2 questions, depending on if there's time for that. One is how much computational complexity you add by doing this with recursive checks or course. And the second is, as far as I understand, is the expectation that was one of the main issues. That if you replace the expectation by the supreme one or some worst case cost, even on the original formulation, the constraint quantities, would that kind of like fix the problem somehow or partly fix the problem?
Yeah. Yeah. Thank you for the questions. I'll answer the second one first. So the question is, what happens if you do a infimum or a supremum over and basically the worst case cost, right? So if you were to use if it was a MDP like a constraint MDP, then that fixes it, but then that becomes a worst case, like robust solution, right? But in a POM-BP, because inherently you have uncertainty over the states, which means you have uncertainty over the cost as well, right? You have a distribution over that. So if you take the worst case, you're basically saying that if there's any probability of your state getting a bad cost, then you're like, doesn't satisfy the constraint, right? So in some way, this solution is in between a totally worst case and like a super optimistic case here. Your first question was about
computational complexity.
right. So POM-BPs in general are like super hard already, right? Like NP hard. They are, I think, like p-space complete. So, you know, in general, to solving them, actually, I think they're undecidable in general, but for this specific type of cases, they are p-space complete. So solving them is already pretty hard. And then now you add constraints, it's even harder, right? But what we found is that because for a normal constraint POM-BP, you have to find over stochastic policies. So that actually adds a lot of overhead in computation. But for us, because we have this, Bellman operator, so we are only slightly harder than normal POM-BP. Just that you have to first, get this admissible policy or like policy that satisfies the constraints. Computing these recursive constraints are not very difficult, right? Because it's just one like, map, like, what do you call it? Like one algebra term.
Thank you very much.
Yeah, thanks for the talk. I was just thinking, do we have similar issues with like stochastic self-destruction with like regular constraint MLPs? Just as in like this like constraint MLP setting? That, in regular constraint MLPs, we have constraints on the expected cost starting from the intra-distribution of the states. But depending on like what happens during the episodes, you might already be in like one state, and you might want to constrain the expected cost from that state, like as we did in the talk. So,
right. Yeah. This is a very interesting point. The yes and no. Yes, in the sense that actually there was a previous result in 1990 something by Haviv, which talked about the unintuitive behavior for constraint MVPs as well for like average reward case. But how it manifests is a little bit different, because here is like we are acting over belief states, right? So it's like, when we are high belief region for like that state, then we don't want the behavior to be like going through these bad regions. So it's like the unintuitiveness is slightly different. But in some ways, yes, because you're also hedging between, if you have low probability of reaching these states, you can say that, okay, I'm just going to take the action anyways and get the high cost, right? So there's also like I haven't fully proven it, but I think you also have a violation of Behrman's principle with constraint MVPs.
Thank you.
Okay, let's thank the speaker again. So this concludes the session, and a reminder again that the town hall will start here in about 12 minutes.